So let's look at proof of lemma 2. So let's look at an edge UV, right? So it became critical, meaning that there was this flow in GF. So you augmented it and this got saturated, okay? And somewhere later, this edge is getting saturated again. That's what it means by critical, right? That in an augmenting path, it is reaching its capacity, right? How can this happen? That this edge UV was saturated in one augmentation, and then you did something more, and later on again UV is becoming saturated. How can it happen? VU lies in shortest path somewhere in between, right? Because this UV, the moment it got saturated, it is out of the picture in the residual network. How can it enter here? Because somewhere here, because this is part of shortest path. So somewhere later, maybe in F double prime, there was this VU edge which is part of the shortest path. Okay. Now I am going to use all of this to show that the distance from S to V will actually increase by at least 2 between these two augmentations. Okay. So we will claim, or we will prove in F prime, distance from S to V will be greater than or equal to whatever its distance was in S plus 2. Okay. This is easy to prove. We will just go through. It's again a bunch of inequalities based on whatever we are using lemma 1. But does this give you something? What we want to show? What is it we want to show? That one edge cannot participate in too many critical augmentations, right? Suppose I show this. What happens? Maximum length of your ST path, right, for any vertex can be n, right? It starts with 0, at least 0, and every time when you move from, so you do one augmentation, you do another augmentation, this distance in the residual network increases by 2. So it can start with 0, maybe 2, 4, 6, 8, eventually it cannot go beyond n, right? So how many augmentations are possible? N by 2 roughly. Okay, roughly n by 2 plus 1 minus 1 something, but roughly n by 2. So if I show this, I'll be done. The same edge, if it gets critical again, it's because it got flow shortest path augmentation through the reverse, and I will argue that the shortest path length from S to V in your new flow network, residual network, increases by at least 2. How do I show this? Well, let's write this down and we'll see. Well, df prime SV, the shortest path from S to V, is equal to, because UV is part of the shortest path, right? Because we've looked at the edges become critical, means that this is we are always augmenting through shortest path. Okay, df prime of SU, we know by previous lemma that, okay, or let's just write greater than or equal to df double prime SU plus 1. Why? All I am saying is in F prime, its length is greater than or equal to whatever its length was in F double prime. Why is that? Lemma 1, very good. Because of lemma 1, this is true, right? Now, but the length of in F double prime, if you look at the picture, VU is part of the shortest path. So this is equal to df double prime SV plus 1, so it's plus 2. All right, because this was the shortest path, it went like this. So to get to U, you got to V and then plus 1. So, this plus 1 gives me plus 2, but df double prime SV by again by lemma 1. So, this is by lemma 1 by shortest path property, and df double prime SV by again by shortest path property is df SV plus 2, and that is what we want to show. Lemma 2, because between every successive times an edge becomes critical, the shortest path length increases by 2. So, it cannot become critical more than n by 2 times. That is for every single edge, the number of edges is m. So, each edge can be critical in mn times, mn by 2 times, and in every augmenting path there is at least one critical edge. So, number of augmentations cannot be more than mn. Okay, I am using big O here, and each augmentation costs order m. So, overall running time is m square n. Okay. So, it is a very natural heuristic to try and do shortest path, and somebody has to actually sit and prove that it works in so much time. This is not the best algorithm. There have been improvements to this. If you know, Carmen's book itself has an improvement to this, to mn square, for example, and so on and so forth. So, there are you know, this is a very well studied problem, and because of its applications there have been a lot of improved algorithm, but for our purpose, you know, at least we have seen one algorithm which runs in polynomial time. Okay. Okay. So, I think I will we'll end network flows with that. We have seen some polynomial algorithms, we have seen a lot of applications, and so I want to just set the stage for next week's lecture now. And so, we kept mentioning about polynomial time algorithms. Okay. So, let's just take stock of what sort of problems you've seen, what algorithms, how much time we know, right. So, let's, you know, what is the first algorithm you would have seen? Maybe for sorting, how much time does it, you can sort in numbers? N log n, right. What sorting algorithm will do it? Merge sort, quick sort? No. Okay, quick sort is not. Worst case it could be n square, but you know, merge sort, heap sort, there are a number of sorting algorithms can do it in n log n time. You have looked at shortest path, right. In the case of unweighted, you just do BFS, which takes m plus n, and in case of weighted, there are issues about where the weights are negative. Let us assume, suppose they are all non-negative weights, then you can apply Dijkstra's algorithm, and how much time does it take? Yeah, so it's, you know, if you use some heaps, Fibonacci heaps, some very efficient heaps, you can actually get the running time to m plus n log n. And today you saw minimum spanning trees, again something like m log n. We have seen network flows, you know, some n square n or something. So, one thing common about all these algorithms is that the running time is some polynomial in the input size, right, order some n power c, where c is a constant. What do I mean by constant? Independent of n, it's like 2 or 3 or 4 or 5 or 100, doesn't matter, it's a constant. It doesn't change when n changes. Is it true? I mean, for sorting, it doesn't look like n power c. Is it a polynomial time algorithm? It's bounded by n square, exactly. So, you know, you shouldn't get worried about log. Log is even better, right? So, it's still polynomial time algorithm. Okay. But let's look at a problem like is the graph Hamiltonian, right? So input is G, and the question I have is, no, let's do this. Is the graph Eulerian? What is an Eulerian graph? What's an Eulerian graph? Each edge is visited every one. So there, okay. So what is an Eulerian graph? It should come back to the same vertex. That's the answer, right? What is an Eulerian graph? Right? It is a graph which contains a cycle that visits every edge exactly once, right? Okay. Theoretical computer science, mathematics, right? You should be able to say this more precise. So, what is an Eulerian graph? It is a graph where there is a cycle which visits every edge exactly once. It's a simple cycle. I mean, vertices can be repeated, but edges cannot be repeated, right? Now, can you check? Is there an algorithm to check whether the graph is Eulerian? It's there in problem sheet 1, which you are all supposed to have seen and done. And do you know any characterization for a graph to be Eulerian? Some nice simple property which you can check? Very good. Each vertex should have even degree, right? So, clearly every vertex should have an even degree, because if you have a vertex with odd degree, the cycle comes through this, maybe it goes out, how will it ever come to this edge at all? So, it is a necessary condition, but what is nice is also it is sufficient condition, that if it happens, right, I want you to understand this necessary and sufficient, if and only if, right, we have seen a lot of these examples, max flow min cut, or that elimination, if and only if this happens kind of thing. So, a graph is Eulerian if and only if every vertex has even degree. So, if I want to check whether a graph is Eulerian, well, go to the adjacency matrix, look at the degree of every vertex and see if it is all even, then you can say it's Eulerian. Otherwise, you know it's not Eulerian. If you really want to find the Eulerian circuit, there is a linear time algorithm which can actually do this walk and do some search method. You can find it in linear time, right? So, there is a order m plus n time. But suppose I ask, is the graph Hamiltonian? Do you know an algorithm for it? Let's do something else first. Suppose I ask, is the graph bipartite? How do you do? Graph coloring, okay. How do you do graph? Do a BFS, right? Just do a BFS and then what? Okay, so you run a BFS, alternate levels get different, 0, 1, 0, 1, 0, 1. And if you find an edge where both endpoints are colored the same, then you know it is not bipartite, otherwise it is bipartite. Problem sheet 1, okay. You've done this, you know it, okay. And how much time you need? Just linear time, right? BFS, and then you have to run through every edge to check that, and this, and you need a proof of correctness, by the way. It's not obvious. Why is that enough to show that it's so? What is the definition of a bipartite graph? What is the bipartite graph? Between a pair of vertices in the same set, right? A vertex set can be partitioned into exactly two parts such that there are no edges within each part. So, if you do a BFS and if you manage to successfully color this, what are the two parts? You have to give me the two parts, right, to show that it is bipartite. All the vertices with color 0 are in one part, all the vertices in color 1 are same part, other part, and you ensured that there are no edges within each part, right. What is the characterization for a bipartite graph? Do you know another nice property of bipartite graphs in terms of cycles. There are no odd cycles. Again, it's an if and only if. That's what makes this very interesting, right? Clearly, if you have an odd cycle, you can't color it with 2, because if you put this in one part, if you put this in, you are forced to put this in the second part, and this vertex is stuck. Okay. So, if you have an odd cycle, it is not bipartite. But the converse is also true, that if there are no odd cycles at all, then there is a way to split it, and BFS and this thing will do it. Okay. So, you have a linear time algorithm. Good. So, there are a number of problems where we have linear time, n square, n cubed kind of algorithm. But if I ask, is the graph Hamiltonian? Do we know any algorithm? So, you have, so come again, so say it again. Remove a vertex, okay, or remove a subset of which subset? Some subset, okay. Number of connected components remaining in the graph, okay, and you have removed some subset of vertices, and there are some 3 components. So, let us say you removed 3 vertices, but there are 4 components, then it is not Hamiltonian. Is there a theorem? You have read this? Okay. So, I think Meghna talked about Hamiltonian graph, some sufficiency conditions, some necessary conditions, some sufficiency conditions. What we do not have is a nice necessary and sufficient condition we do not know yet. What do I mean by nice? Something which we can check easily, right? We do not know a nice condition to check whether a graph is Hamiltonian. But so, what is a Hamiltonian graph again? Yeah, what is it? What is a Hamiltonian graph? It's a graph that contains a cycle that visits every vertex exactly once, right? You can omit some edges, doesn't matter, but you have to visit every vertex exactly once. If there is such a cycle in a graph, then it's a Hamiltonian graph. Now, can somebody give me some algorithm for the problem? Brute force, just by using the definition. Okay. So, my graph has n vertices. Let us give 1, 2, 3 up to n. Some algorithm, some backtracking dynamic, whatever kind of an algorithm, but we need to analyze it, and it has to be correct, and I want to check whether the graph has a Hamiltonian cycle. Oh, you want to find all paths from vertex 1 to 1, okay, and see whether it visits every vertex. How do you find all paths? I want a 3-line program. Correct, we can analyze it. And if you are going to do DFS, you are going to spend linear time. I am telling you, there is no efficient algorithm actually. So, here is my algorithm, right. So, what I am going to do is, so there are, let us say 5 vertices. I will illustrate it by a simple example, right. There are 5 vertices in the graph. So, I am going to say, here is my Hamiltonian cycle. Okay. So, my vertex set is 1. So, something like this, and I am going to say, is this a Hamiltonian cycle? Okay. So, 1 to 2 to 3, 2 to 3, 3 to 4, 4 to 5, is it a Hamiltonian cycle in this graph? No, you can test it on any graph. Yes? No? Why not? Because there is no edge 1, 2, right. So, I am providing you, here is the cycle, start from 1, then go to 2, then go to 3, then go to 4, then go to 5, and come back to 1, right. And you say, no, it's not a Hamiltonian cycle because 1 to edge is not there. Oh, I see. Okay, so I'm going to change now. I'm going to say 1 to 3 to 5 to 4 to 2. Is this a Hamiltonian cycle? No, because 5, 4 edge is not there. Okay, I'm going to try. You see what I'm trying? What? All permutations of 1 to n. Check whether it's Hamiltonian, whether there is an edge between every adjacent pair or not. How much time? Is this the algorithm? Is it the correct algorithm? Clear algorithm? Right? There's no chance of any mistake because I'm just trying everything. Right? So for every permutation pi of 1 to n, check, if pi I plus 1 is an edge for all I. You know what I mean here, right? So you just take the permutation, look consecutive things, and see where they are edges. How much time does the algorithm take? N into n factorial. Okay, so here it is. Nobody can question the correctness of this algorithm, right? Because whatever you tell me, like, oh, take the subset, delete it, and I don't know whether it's correct. I have to, you need to prove some theorems here. Absolutely, it's a correct algorithm, clean, simple algorithm with running time. I have analyzed it. N into n factorial. Okay. Unfortunately, for the most general graph, we don't know much better. There are some better algorithms. We will see next week some slightly better algorithm, but its running time is not of the type I said n to the c, but it is more like n factorial. Okay, we will improve it next week, but at best I will get to 2 power n. Okay, I will improve it to 2 power n, but it is still not of this type. Okay. So it is not a polynomial. The running time is not a polynomial in the input size, but it is exponential in the input size, because as n increases, so it's actually n factorial is more like, n power n, right? It's like you can show that it's greater than or equal to n by 2 power n by 2, because the last n by 2 terms are all greater than or equal to n by 2. So clearly, right? If you really want to look at it in terms of exponent and so on, this is easy to show. Right? Just take the n factorial, look at the last n by 2 terms. Each term is greater than or equal to n by 2. So it's at least n by 2. So it's like n is sitting on the exponent. As I said, we will improve it. There are slightly better algorithms, but unfortunately, all of them have n sitting on the exponent. Okay. Now you can ask, so what? Right? Computers are powerful. You can big deal about exponential algorithms. Let's do some calculations, right? So suppose I have an n cubed algorithm, and I have some 2 power n algorithm. Okay. And I run it on an input of size 1000. So this n cubed algorithm will take 10 power 9 steps, and this one will take 2 power 1000 steps. Okay. What is 2 power 1000? Let's write it as 2 power 10 is 10 cubed roughly. Okay. Let's do this approximation and say that it's 10 power 300. Right. 2 power 10 is 10 cubed. So 2 power 10 power 100 is 10 power 300 steps. Great. So now how many steps, how many instructions can your laptop or the most powerful computer you have can do in 1 second, do you think? 10 power 9 or 10 power 10. So our current best computers can perform something like, let's assume for 10 power 9, not much more than that, 10 power 9 steps in 1 second. So this algorithm will take 1 second for me, and this algorithm will take how many seconds? Or 10 power 290 seconds. Right? There is a saving of about 10 power. You just divide this by 10 power, let's say 10 power 10, right? So it's 1 by 10. So assuming 10 power 10 instructions per second, even just for a problem of size 1000, This algorithm will take much less than a second, and this algorithm is going to take 10 power 290 seconds. Ooh, how many years you think? Or you can do some quick Google search. I think I've checked sometime. 10 power 10 seconds is like about 350 years or something like that, or maybe even more. Okay, just approximately. So this is like just for a problem of 1000. Okay, now we are not even going to talk about 10,000 now, right? Whereas for a problem of 10,000, this guy is going to be even very good, pretty good, right? If you have 10 power 4, then this will be like 10 power 12. So assuming 10 power 10 seconds steps in 1 second, this will run in 100 seconds. This will run in 100 seconds for n equal to 10 power 4, but we don't even want to talk about this algorithm, right? So because, and n factorial is even worse, by the way, right? Because it's even worse than 2 power n, okay? Okay, so you can say, if the problem is so important, I will run parallelly, put in some 1000 computers in parallel to try and solve this. Okay, so it won't take 10 power 290 seconds, so you take off a 10 cubed out, and so maybe 10 power 287 seconds. Big deal, right? Doesn't matter. So what's the point? The point is that these exponential algorithms are not useful at all. That's why polynomial time algorithms, are associated with feasible computation. Now, there is one little problem. Even n power 100, I would call it polynomial, okay, which is little unfair. But most polynomial time algorithms are like n power 5 or 6 or something like that. And but so what? I mean, now we don't know is the problem. So we mentioned about Hamiltonian problem. To check whether a graph is Hamiltonian, I said pretty much we have only about 2 power n or 1.5 power n kind of an algorithm. What does it say? Is the problem hard, or are we stupid that we have not found an efficient algorithm, right? It could be one of the two. The problem may be very hard, or maybe we haven't understood it enough that there may be a better algorithm we have not come up with, right? So what would be nice to argue is that to show some lower bound on the running time. Suppose I want to show that no algorithm can do better than n power 100. Then if I can prove a theorem, right, it's not just some heuristic. If I can prove that any algorithm to solve this problem will take at least that much time, then I would have at least shown that the problem is hard. It's not me, it's just the problem because I have this theorem, but we don't know that also. Okay, so we don't know so Hamiltonian cycle is not the only problem. Okay, so let me just give another example. Find the minimum vertex cover in the graph. Right, the input is a graph. I want to find the minimum vertex cover. Suppose I know that the graph is bipartite, then I can do something. What can I do? Find a maximum matching. How can I find maximum matching? Oh, network flows, right? I can, n cube time, n square time, I can find maximum matching, and Koenig's theorem tells you that from maximum matching you can actually obtain minimum vertex cover. You can solve it in very efficiently polynomial time. But suppose the graph is pretty general. I don't know whether it's bipartite. It's a general graph. Then we don't know. We don't know nice characterizations to solve this efficiently. Okay, but what would be a brute force algorithm? No, permutation is not the thing here. All possible subsets, because the solution I am looking for is a subset of vertices, right? So try all possible subsets of vertices. Take a subset, systematically enumerate all subsets, and go and check whether they cover all edges. Run through your edges and see whether every edge is one of the endpoint is there. How many subsets of 1 to n are there? 2 to the n. Okay, so Hamiltonian was like n factorial. So this gives you 2 power n algorithm. There are slightly better algorithms. Again, we'll see next week. But unfortunately, n is on the exponent in all the algorithms we know. Okay, there is no polynomial time algorithm, so that also suffers from this kind of a problem. Okay, so So there are a lot of things known. So in the last 25-30 years, one, we know now about hundreds of thousands of problems of this type, which are very hard. We don't have an efficient algorithm. We don't have a lower bound on the running time. So they are hard. We need to do something about it. We can prove some equivalence among them. That's one nice thing, right? We saw, for example, Megan, I was talking about reductions, right? If you want to find a number of edge disjoint paths, you can reduce to network flows. So if you solve network flows, you can solve edge disjoint paths. So similarly, I can give some reductions. Oh, if you solve vertex cover, you can solve Hamiltonian city problem, right? Hamiltonian graph problem. So we will talk about this whole notion of NP completeness, using which there is this relationship between these problems are known. So we'll see that. That will be one big chunk of the next week lecture. The other, so that they will give some evidence that these problems are actually really hard, because there are thousands of problems. We will have been working hard and they are somehow related to each other. So it must be somewhat hard. So that's one evidence. The second thing is that, so what if they are hard? The problem doesn't go away. I need to solve it somehow, right? Because many of these problems are actually practical problems. So the next topic we will look at is how do we actually practically solve some of these problems. We will relax some constraints and then do something and see how best we can get out of it. Okay, I think I will. So that's sort of an overview of what's coming in the next week. Okay, so I will stop here. I think so. So this week is sort of a run of a lot of efficient problems for which we know efficient algorithms, shortest path, network flows, connectivity, cycle finding, all kinds of things, and we'll get to hard problems next week.